Okay, so this is the third tutorial session for the NPTEL online course on mechanism and robot kinematics. And I'm G.R. Krishna Sanabdhar, TA for this course. So today, as we had discussed last time, we would be discussing and reviewing some of the aspects of week 2, partially of week 2, and also some parts of week 3. And as we planned, we'll have our MATLAB sessions today, wherein we'll learn how to code MATLAB or GN or Octave sessions today, where you would be learning how to solve numerically certain problems in dynamics. We'll start with some simple examples and then we'll move further. Okay, so let me start with Grashof theory. So this was discussed in the week 2 of this course, or Grashof's criteria. Okay, so it's Grashof criterion, so to speak. And it is defined for any kinematic chain consisting of primarily which can be four-hour chain or a derivative of this 4-hour chain. So as per Grashof criterion, say given we have this this here, there's a 4-link chain, and say we have this is L min and this is L max. There's some P and Q. So L min and L max are the lengths of shortest. So L min is length of shortest link. L max is equal to the length of longest link. And L min and here P and Q are the lengths of the other 2 links. Right? So as per Grashof criterion, we had L min plus L max should be less or equal to P plus Q. So this is the criterion as per Grashof. So if this is there, if this condition is fulfilled, then we can have some sort of a crank in the mechanism, or in the 4-hour chain. So now let's talk about these 2 things. What is crank? So we'll always keep on talking about what is a crank and what is rocker. So Grashof criterion specifically tells us about the presence of a crank in the mechanism, right? Now, what is a crank? So crank is in such mechanism is any link, say some connected in some mechanism which can rotate completely. So it is a link which can rotate completely. So this is what we call as a crank. And rocker is a link in a mechanism, some link in a mechanism, which can only, it can only make some constraint motion. So only till certain points. So this is the left end and this is the right end. So it can only oscillate between these 2 extreme positions. So what is a rocker? It is a link which can partially rotate or we can call it that is equivalent to, which can only oscillate between two extreme positions, so to speak, right? Two extreme positions. So this is what we call as a crank, and this is a crank, and this is a rocker. And apart from the third that we can have is what, just some stationary link. So yeah, that's not something of interest to us. On the third, I mean, you'll always find the talking is what you call as a ground link. So ground link is a link which we fix. We fix the link, or maybe rather the other way is that we constrain the link. We constrain the link from so as to have no motion. Or simply it's just that we are fixing it, right? Now let's go back to the Grashof criterion. So we had this link here, and this 4-bar mechanism. Mm, I just wanted to not be obvious that something is largest. Some other link. This is the shortest, so just to have, yeah. So now it's Lmin, Lmax, P and Q. So Grashof criterion for existence of crank, we have of at least a crank is that we have Lmin plus Lmax is less or equal to P plus Q. Now let's look at some cases. So case number one. So case one is, say we have Lmin is fixed, or Lmin link, right? Lmin link. Let me just call it Lmin link. So it indicates that smallest link is grounded, which means we are not allowing any motion to take place here. Okay, so let me put it here. So this is grounded. And these are all revolute joints. So I forgot to mention that R indicates that it's a revolute joint, which I'm sure you will be aware that it's a joint with just 1 degree of freedom, right? Which only allows rotation motion, isn't it? So what happens is, if this shortest link is fixed, and mind you that this can rotate like this full circle it can take, and at the same time this can take another circle of its own, right? So it means this link, let me call as this grounded link as 1, second, third, and fourth. So what's happened is the second and third can rotate completely. Now you imagine that this is moving, right? So if it moves, then it will be something centered at this point. It will be moving at this, some sort of like this, it will take a full circle. And this also will be taking a full circle about this center. So which means that links second and fourth can rotate completely. And they are nothing but these links are adjacent to Lmin. Now you'll ask, okay, but what about third? So third link can only partially rotate. It will oscillate. So it means that here I forgot to, it's a link fourth. So link three can only oscillate. So as it moves, it will just keep on oscillating about this position between certain extreme ends, which is essentially determined by the difference in as well as their orientation. So it is that it can only oscillate between two extreme positions. So which means that 3 is a rocker. So you have, this is the case for when L mean link is grounded. Now we come to case 2. I'll just copy this diagram here. Yeah. And here what let's do is, now let's ground any link adjacent to L mean. So we have either P link or L max link. Since these are the two links which are adjacent to L mean. Now let's say we ground P link. So this is grounded. Now let's see what all extreme positions can this take. Now this, now let's say L mean this is say, so there's what do you call, so say some trajectory that can be, it can take the joint, so to speak, right? This R joint connecting links L mean and L max. So it can have this trajectory. So what it will say, it moves here. Let me just so it moves here. Then what happens is this link here, it will move slightly, also keeping the length constant. So this will be the new configuration of this link. As it moves down till here, it will just move to some position here, this link. And once it starts getting back, right? So what happens is, say at this point, say if when this link reaches till this point, then link Q will reach some extreme position. And as it moves further, it will start going back. Right? Say if we have here, then say if we have the link here, right? And then what happens is, so it will have some sort of a this, and then it will some sort of a, it will just crisscross. Then you'll have this, and as you move, right, it will just start going back in this form, so that only the small link rotates completely. So in this case, SL min link rotates completely. This means that it is a crank. Right? And so that is what a crank is, and it will never be able to cross this line here. So this is like crank, and then let me talk. So Q link is a rocker because it will just oscillate between two extreme positions. And likewise, even L max link is a rocker. And this rocker, uh, so any what do you call yeah. So this Q here, actually we call Q as rocker, and this is a crank. So this Q here will never cross this line here. The rest of these bodies will always just rock with respect to, but Q will never cross this line of frame. We call this as a line of frame. And this is the case with case 2. And even if we fix say L max, we would see the same, that the shortest link will rotate completely, and the largest and the other link, which is Q, will just oscillate between two extreme positions. So that is what we call as a crank rocker. So here with one we call as rocker, and this we call as crank, just by nomenclature. For Lmax, we don't give it a name, although it happens to rock. It's just that one of its ends does not remain at any fixed position, unlike Q. So I think that is the notation what I have seen is used everywhere, that since one end of Q is fixed, so that's the reason we just call it rocker. But Lmax, the link will also keep on oscillating. But since both its ends can move, we do not give it any name call. So this crank and rocker, the requirement, I'll put it here, is that one end. So the thing common to both is both crank and rocker have one end fixed. And that's what is from the observation that I have seen. Just I think this helps also in to keep things in perspective and to decide what you should call a rocker and what is. Although if you talk about rocking motion, then even Lmax link goes rocking motion because it just keeps on jumping with respect to the other links. And so far, what we have been talking is what we call as inversions, right? And I just failed to mention here. We call it inversion. So inversion, what happens is in inversion, we fix any link. We fix any link and say provide some input to one link, and we just keep on monitoring how the other links will behave. So in this case, say what we did is we rotated say link 2 and was also observing how link 4 behaves. So in that sense, just to give you a what do you call something before we really talk about it. So this will call as an input or input link or input actuation. So it's like some actuation here. And this where the motion of this we are calling, that's what will be monitoring, is essentially just the output of I mean, the output that we would like to say record, right? So once we have case 2, now let's come to case 3. That is another interesting story here. So case 3. Now in case 3, Sometimes just a moment again. Let me try once more. You have to. Mm, mm. So this is Lmin, Lmax, P, Q. Now what we do is in the case 3, we ground the link opposite to Lmin. So this is what we do here. So in this case, it's just unique. So which means that essentially we ground Q link is grounded. So that's essentially what we do here. Right? So now what we have is we ground this. Now say we are so what happens is this and this, right? When say we use this as input and this one we say output, so to speak. So what happens is in its extreme situation, let's look at how things will work. Or maybe I could have just drawn here itself. So say F, let's look at this length, Lmax link, right? So it will have some sphere here. Just imagine that it is reaching here. Imagine Lmax reaching here. And say this is stretched, just for imagination. The thing is Lmax plus Lmin will be greater P plus Q here. If it reaches this part, say this reaches here, right? And Lmax reaches here. The thing is this, as you know, is not possible. I'm just imagining this, giving a thought experiment. Say Lmax reaches till this point, and say this node, this joint here reaches here, and say this length is P, right? And we already know the length Q. Then from the from say equality, what we would have is, we would have that Lmax plus Lmin should be equal to P plus Q. But the thing is, this is just an extreme case. In general, this is how it is less or equal to P plus Q. But in general, what will happen is Lmax plus Lmin is less than P by Q. But this requires that Lmax, sorry, like this says this thing. And as per the requirement of Grashof criterion, we have Lmin plus Lmix is less or equal to P plus Q. And if we remove the equality part, which is just a special case, we will have that L max is leader, which is just contradicting with each other, because of which L max and P links cannot rotate completely. The thing is, otherwise it will just violate certain condition, the length condition, which means that this simply implies that L max and P links, I'm just calling links by their lengths, right? These are rockers. So which means that L max will reach certain value and then go back and oscillate certain value. It will just lie between two extreme cases. It won't go beyond that. Likewise for P link. So which means that this mechanism we call as double rocker mechanism. And this mechanism we call as crank rocker mechanism. And this here will be double. So it's double crank mechanism. Now let's talk about one special case. Have one N fixed to the ground link. That is what I should mention here. Otherwise, it sounds very vague. To the ground link. Then it makes sense. Right? Now let's talk about one special case. The question always arises. What if by design L max plus L min is equal to P plus Q? That will often say we have such cases, say such if we can have such case like this. But a special case for which this holds is a 4-bar parallelogram mechanism. Something like this. Right? It's say link 1, link 2, link 3, link 4. And here this link is equal to this link, and this link is equal to this link. Now say we fix, in this case it's a this is a special case, right? Special case. So we fix 1, the link 1, right? Link 1. Now once we fix this, so we allow say link 2 to rotate, or we provide actuation to it. And now in this case, what is happening is, if we clearly look at what we are doing here, let's use the degree of freedom analysis to find the degree of freedom that system can have. Let's say in this case, number of links that we have is 1, 2, 3, 4, which is obvious. Number of joints that we have is 1, 2, 3, and 4. And all of them are revolute joints. Now let's just determine the number of degrees of freedom, total degrees of freedom of the joints. So it is every joint is a revolute, which means 1, and all of which happen to be revolute. So it is 1 cross 4. So it gives us 4. Now the formula for degree of freedom is F is equal to 3 NL minus 1 minus 3 NJ and plus summation Fi. After putting values, we have 3 into 3 minus 3 into 4 plus 4, right? And 9 minus 12 minus 3 plus 4 is 1, right? So here we have 1 degree of freedom. Now I'll ask, okay, let's see what 1 degree of freedom. What we can say is this link here, link 2, it can freely rotate about this. And if you go by that, say, Grashof cases, right? So this is the shortest link, and this link is adjacent to the shortest link. So which case this is? By from this logic, we have crank rocker mechanism. Fine. So which means that one of them will be crank, right? And as per we know, the shortest link is always crank. So this is always a crank. Fine. Now, if you go by that, then you ask, okay, but the thing is, this is a crank. Say this is a crank, right? Then say so and then we have degree of freedom as one only, right? It's as per our analysis, the degree of freedom is one. So which means that if we rotate this, and since we have full control over rotation, and it can rotate completely, which means that the motion of 4 of the link 4 just happens to be known just because of this. So which means that the motion of link 4 is not a degree of freedom because it can be clearly defined by the motion of link 2. And say when this reaches here, so this will also reach here. And you'll find that they just form a concentric line, so to speak, a collinear, so what we call it, it's a collinear line, right? I mean, all these points are collinear, so to speak, all these joints. So all these joints fall along a line. And as we move here, I mean, as we say, bring this link number 2 to this position, then we say that even link 4 is able to reach a position down, I mean, somewhere here. And which means that even link, and when we completely rotate link 2, even link 4 rotates completely. So this is a special case in the sense that we have 2 and 4 are both cranks. And it deviates from the case number 2 that we had. So this means it is a double crank mechanism. But only because L min and I mean, the length of links 2 and 4 are both the same, as well as, and both are small, and links 1 and 3 are of the same length, and they are both large or maximum, right? So it's a double crank mechanism. Right? And here the requirement, what we see is the length of L2, L1, say L1 is equal to L3, and L2 is equal to L4. This implies that largest, say smallest is L1 or L2, say L1 or sorry, L2 or L4, and plus L3, we can choose either one. So say L1 I'm taking, this is the same as the other links, which is say 3 plus 4. Now, but you say fine, now what? Can we have another different case? Because in this, even for this satisfying this requirement of L min plus L max is equal to P plus Q. There is one configuration which satisfies this. Say we have this, and also in this case, even if we were to constrain the smallest link, it would still have a double rocker mechanism. This is just a special case for parallelogram. Even if we're to constrain this, it would still be able to do that complete rotation, even if we were to ground this link 4. So this just applies here. Okay, coming back. So say we have this mechanism here. So in this case, this is say first link, second link, third link, and fourth link. Here, link 1 and link 2 are equal, and link 3 and link 4 are equal in length. Now, say we constrain any one of them. Say we constrain to 1. Which means that, and let it
say since these are of equal length, by rotation, when we rotate link 2, it will land up here, and this link will also shift here, isn't it? And you'll see that the joints of joint connecting links 2 and 3 will be coincident with joint connecting 1 and 4, and this link here will reach at this point. And say if we move further, say this link moves here, link number 2. I'll just use a different color so as to not confuse. So this links here. So which means that link 3 will be, it will just, right, it will just cross each other. Right. So in this case, what happens is, and let's just keep on looking. So say this reaches here, then the other link will also reach here. So which means that even in this case, 2 and 4 are cranks by virtue of, and we clearly see that L2, the lowest is L1 or all L2, either one of them, plus largest is L3 or L4 is equal to L2 plus L4, right? So both this is also a double crank mechanism. Right. So this is what we were trying to do here. Now, in general, if L min plus L max is greater than P plus Q, then it would never be, it would always be, it would never be, it will always have be a rocker mechanism. Like it will never have any other in this scenario. Right. So this is what we are trying to do. And so what we'll do is, let's also talk about displacement analysis. That was the second part of what we were trying to learn today. All right. So in displacement analysis, the goal is, I'll just again redraw that this 4-bar mechanism, right? And as I mentioned, say we ground this mechanism, this link here, and say this link 1, link 2, link 3, link 4. And we say allow link 2, we provide some input by some actuator, right? Then we say we provide rotation here. We want to look at the rotation of link 4, like how much, say this is theta and this is phi. So we want to say that given theta, determine phi. So this is what we are aiming to. So essentially theta here is an input and phi here is the output. So in displacement analysis, that's what we aim at, right? Now, mechanism, the whole purpose of a mechanism is to convert the input that we provide to it into some meaningful output. Now, in this case, we provide theta as input, we want some output. And as in the lecture we had discussed, right? So we had, say, a pair of Caesar.
right? So something like this we used to have. I hope I'm drawing right. Okay. Uh, Witness. So this is the joints here. So we will have this, it goes, and then comes out. Okay, I think I'm drawing the opposite way. Yeah. So you have this, say this, and say some way this will also have certain thing, right? Something like this. I'm sure it's not a good drawing, but still. So say we are providing some theta here, right? Theta between these two Caesars on the input side, and then this is where we have fear. So essentially, this is how, in general, any mechanism, the whole purpose of a mechanism is, say we provide some input, we want it to give us some desired output, which can be made to do some useful work. So even in Oldham coupling, right? What we do is we have one torque bar here, and then what we use some coupler and then transmit it to another this torque bar, this torque to another shaft, so to speak, through this coupling mechanism. This is a coupler. So in this case, what happens is, say any theta that we give here, we always want the same theta to be even sent out to the output. So this is input, and this is output. In this case, it's very straightforward because they happen that the coupler transmits the same what do you call rotation, provided they are of equal width. I'm sorry, equal diameter. If it is different diameter, and if we are using some differential coupler, then it can be used to reduce the intensity of the rotation. So you know about all this conservation of linear momentum, angular momentum, right? In this case. So but from the conservation linear momentum, we will want to only have that equal, but rest we can dissipate based on our the way we have our what do you call the differential uh, coupler here, right? So based on this, we have two analysis that we tend to do. One is what we call as forward kinematics. In forward kinematics, what we do is, and what I have been dealing so far is, the way I was talking about is all about forward kinematics. But it's not that that is the only way. So something I had drawn this way, right? Something this. So this theta I'm giving, I'm looking at some phi, this is grounded. So which means that this is input and this is output. In forward kinematics, we aim at determining for a condition, for the situation when given some input theta, find some output. So that is essentially what forward kinematics is. It's as straightforward. And inverse kinematics, from its very name, and you can easily guess that, say we require this link here. I'll name it again. The fourth link, you want it to be fixed to some theta has to be fixed. And you are fixing it just, I mean, in the sense, sorry, not fixed. I'm just using the wrong word here. It says set to some value.
And this is why we are doing this, for certain requirements. Then, and one is grounded again. So we want to know what is the value of theta. So for some set phi, what is the value of theta required? So it means that given phi, determine theta. So this is what inverse kinematics is, that you've given, say, for certain output, what would be the input required to achieve that output. So that is what is inverse kinematics. So they are just, yeah, it's not some, they are not quite different. It's just what we are looking at, which matters here, right? So I think that is what we had planned as per reviewing part, and we'll discuss at length next time also, and provided you all have certain doubts, right? So today what we'll do is I'll also solve certain lesson 2 problems, few, before we move on to MATLAB to do some of MATLAB or Octave. Even I have Octave, so we can use any one of them. Okay. Okay. So let me start with, I'll just be solving some examples here. Not assignment, it's, is it assignment? Yeah, I think it is here. Assignment of week 2. And these are just problems from the quiz. Since submission date is over, I think we can freely discuss about it. So here, I'm just picking up one question, say question number 4. So what does question 4 is, question 4, it says that, say we have a 4-chain mechanism, or 4-hour chain mechanism, sorry. And one is connecting this the ground link, right? So given this x, the length is x, this is L1, this is L2 and L3. And we are given the values that L1 is equal to 12 centimeters, L2 is 8 centimeter, and L3 is 10 centimeter. So it asks us what value of x makes this chain a double crank mechanism. This is what it asks us to do. Now we'll go back and let's determine which case was required, or which case gave a is for double crank mechanism. So we come here to case 1. It says that it's a double crank mechanism. Okay, so we got it right on spot. Okay, so it's case 1. So in case 1, what it says that the minimum link is grounded. So the link of minimum length is grounded. So which means that what we require here is, from the to the answer here, this means that L min is grounded. Hold that. Now let's take a careful look at here. You have L1 is 12. This is 12. L2 is 8 and L3 is 10. And so it means that X must be minimum. So which means that the only way for this to happen is if X is less, either strictly less or equal to, but say let's go with strictly less. If X is less than 8 centimeter, then we will have a double crank mechanism. So that as simple, the answer is as simple here. So it can take any value from, of course, not 0, but anything from 0, say 0 till 8 centimeters. So this is the range of values that X can take. Fine. And yeah, just one problem. I think the rest are all straightforward. If you have any doubts, then please let me know. Otherwise, I'll just be blabbering. Okay, so now let's get on with our business about MATLAB. Or Octave, I always keep on. So I'll just go back to our previous tutorial session and just find out what we are planning to. So this is the notes to our previous session. So we had planned to solve these problems here. Just copy both of them. Come to tutorial 3 and just append it if it's possible. Paste. Yeah, it is possible. Right. So what we'll do is drag this to the end, leave empty. This also drag to the end. And today we plan to open our MATLAB or Octave innings with a simple problem. So our goal is to, it's a planar problem that say a person is throwing a ball with some theta and some initial velocity. And then we want to look to how far it goes, right? And essentially, we just want to plot the entire behavior of how the ball, which path does it take. So that is the goal. So the equations, as you know clearly, is very straightforward here. That along x direction, we have no force because force is the gravity force, which is actually acting vertically downwards. So from the component of linear momentum or force along x direction, we have m is given again as the mass of it's the mass of ball, and this m double derivative of x with respect to time square is equal to 0. This implies that the acceleration along x direction is 0, and along y direction it is minus mg. Along y direction is m y double dot is equal to minus mg. M cancels out, so we have y double dot is equal to minus g, right? And this is essentially the equation of motion. That's what I was doing here, right? And then we have m dx by dt vx is equal to 0 minus g. So we have this solution, this to be done here. And finally, the equations of motion was that d double x is equal to 0 and y double dot is equal to minus g, right? There were certain initial conditions, and we plan to solve it both numerically and analytically today, right? So we had the problem as, so d square x by dxt square is equal to 0, and these are the two, and we require two sets of initial conditions, both for x and y, and then we would be solving it. Okay, so the our equations are, I'll write it again because we want to do some operations here. Now, when we solve it numerically, although we can have different numerical techniques, but since this is not a numerical class, numerical techniques course, I would be using MATLABs or preferably MATLAB today. because so that I mean, if there are any issues, then it can be easily set out, because I'm not very much, I don't use Octave frequently. So if certain issues come, then it will take some time to figure out, which I can only do given if we are doing it, if given some more time, right? But still, I don't know who all have downloaded MATLAB, or say this Octave is a free software. And if anyone wants, then you can just use any search engine and then type GNU Octave and then download it from its official website, right? So anyway, we'll try with Octave right now and we'll see what happens. So we'll use OD45. It is a Ranjekuta. It's a fourth order Ranjekuta scheme, fourth order Ranjekuta time integrator, or you can use for any other purpose, but say in this case it's a fourth order, say integration scheme. That's all, let me put it. Right. However, it takes only first order differential equations, which means that any equation of this form, du by dt is equal to function of u comma t. It only accepts any equation of this form. But in this case, all our equations, this as well as this, are second order equations, which means that we need to reduce it into a system of first order differential equations. And that's what we are going to do. So d square x by dt square is equal to 0 can be broken down into dx by dt is equal to 0, sorry, is equal to vx, which is the x component of the velocity vector, and then dv by dt, dvx by dt is equal to 0. And you see that when you substitute the expression for vx in this equation, you are essentially getting back this. Likewise, this will be broken down into dy by dt is equal to, again, it should be vy, and then dvy by dt is equal to minus g. So you see, we are able to convert our equations into a system of first order differential equations. Okay, so this part is done. The other part that we're looking at is, to run this, we require initial conditions, because that's what OD45 is going to ask us. So we'll say, okay, we will use the following initial conditions. Yeah, it's, if I said boundary conditions, then let me correct myself. It should be initial conditions, right? Initial conditions is that x at time is equal to 0, because x, vx, y, vy are all functions of time, is equal to 0, which means that I'm starting from some point here and then throwing it. I'm assuming that the height of the person is 0. It's just an assumption, because it helps us to simplify our problem. Let's say I'm throwing it from here, right? Or maybe the person is throwing the ball from a very low height, so it's just close to the ground he's throwing. And this is just for simplification purpose. And we'll have vx t is equal to 0 is equal to some value, some angle theta. So is equal to v. So it will be certain velocity. I'll call it, yeah, let me call it capital V. This the magnitude. So he's throwing at some velocity vector whose magnitude is v, and this is cosine theta. And likewise, vy t is equal to 0, and then again, sorry, y at t is equal to 0 is equal to 0, and then vy t is equal to 0 is the vertical component, which is v sine theta, capital V sine theta. And the way we will solve eventually is that first of all, we'll have, so I'll rearrange something like this. It's just for it to look neat. So I'll be using certain this or reorganization of, sorry. Right. So we have, yeah, this is how we'll be implementing our system. And we'll be solving over certain time period. We'll see based on the values. Before that, let me solve it analytically. Let's analytically solve it. So analytical solution. So this will give us some idea. Right. So coming back here, what we have is we had d squared x by dt squared is equal to 0. So which means that dx by dt integrating upon once is a constant. Right? So which means that it will be something. So at t is equal to 0, and this is also remind you this velocity at time t is equal to 0. I mean, it's also called velocity, which means that velocity along x component is 0. Now at t is equal to 0, we have Vx is equal to capital V, which is a fixed number, cosine theta. So in that matter, what happens is that we have V small x is constant. It won't be changing, right? So if Vx is constant, then we can integrate again, and then we have x is equal to x as a function of time is equal to Vx, which is nothing but I'll be using the V cosine theta, which is what Vx is, into time plus some other constant d. Now, at t is equal to 0, x of t or x is equal to 0. This means that V cosine theta into 0 plus d is equal to 0, which means that anyway this term is 0, so which means that d is 0. So eventually, x of t, this implies that x of t is equal to V cosine theta into t. So this is we have done. One equation is solved. Now let's look at this equation is equal to minus c. This implies that dy by dt, say once we integrate it, first integrate upon integrating it first time. So we have minus gt plus some constant c. And mind you, dy by dt is also the velocity. So it is vy, right? So vy is equal to minus gt plus c. Now, what happens is at t is equal to 0, Vy is equal to V sine theta. So which means that minus gt, or so it's sorry, should be just minus g into 0 because at t is equal to 0 plus c is equal to V sine theta. So which means that c is equal to V sine theta, which means that we have been able to obtain an expression for y as well. So y t is equal to sorry, not y, but we have been able to obtain the expression for dy by dt. So this means that dy by dt is equal to V sine theta minus gt. Now we can integrate it again and then look see that y of t is equal to integrating again. We have V sine theta into t minus gt squared by 2 plus some constant e. right? Now, again, we'll use our condition that at t is equal to 0, y is equal to 0, which means that this term is going to be 0, this term is going to be 0. So which means that even e is equal to 0. So we can drop it out and we have this as our solution. So this we have our analytical solution. And why we require analytical solutions? Just so that we can have, say compare our results with the value that we obtain numerically. Right? Just that's the reason we are going to have. Now let's consider these expressions here. Let me only write the final expression. So x of t is equal to capital V cosine theta of t, y of t is equal to V sine theta t minus gt squared by 2. Right? So this is the one. Now say we have launched or say fired this or say threw the ball in space. So it will follow some trajectory and then comes back. So which means that as it flows, the x will x. So and then also that Vx is equal to is a constant always. And then Vy, which is the velocity along y component, is V sine theta minus gt. So here we see that the y component of velocity depends on time, and that also with a negative sign. So which means that it just keeps on getting subtracted from the initial velocity, which means that it's going to decrease as we travel, right? Now let's just take a look. Right? So we started from here. X component velocity is always the same. So say it was this, say this some indication of magnitude, and this is our vertical velocity. So it will just keep on decreasing. And at the highest point, it will just become 0. So at this point, what happens is Vy is equal to 0. This implies that V sine theta minus G, I'll call it T m, means maximum height, is equal to 0. So which means that T maximum height is equal to V sine theta by G. Right? And again, as it drops, then V starts increasing again. And now it's just because now as we moved on, what happened is now everything from this point, now velocity was 0, but from here onwards, everything starts from minus G into T minus Tm. So it means that this is a value which keeps on increasing and it's multiplied by G. So the velocity will keep on increasing till it lands here again. At this point, y t is equal to say some t final tf is equal to 0. So from here we can get how long did this system take to travel the distance. I mean, did the ball take it to return to the ground? So which means that from here we have V sine theta, which is a non-quantity, into Tf, a non-quantity, minus G Tf squared by 2 is equal to 0. We solve this quadratic equation and then get the value here. Now, anyway, what you'll do is let's solve this quadratic equation. So let me do is I'll just take take it to the other side. So you have Tf squared by 2 minus V sine theta Tf is equal to 0. And then multiply by 2. So we'll have this 2 gone. So we'll have 2 and then divide by G. So we have Tf squared. So we have
TF squared minus 2V sine theta by G is a constant value into TF is equal to 0, right? Now TF, we can factor it out, and then we have TF minus 2V sine theta by G is equal to 0. Now, from here we have two conditions, either TF is equal to 0 or this part is 0. Again, TF cannot be 0, like we cannot return from it where we started, right? As this means that we have simply not thrown the ball. So which means that T final is equal to 2V sine theta by G. So now you'll ask me, okay, but why are we doing all these calculations? The reason is, I'll just call it max. The reason is because it helps us to get an idea of how long we should simulate or we should do the simulation. Rough idea. Okay, so now let me share the screen for laptop screen. So I hope I'm able to share, or let me share again. Still, I think now I'm able to share. Okay, yeah. So let's start coding it up. And again, for more details, please just ping me at later time. But today what we are going to do is we will be writing a code. So this code is, I'm sorry, there's a very, I need to preferences and then editor. Let me increase the font size. Okay, where is it? Editor styles I have. Normal general, what does it say? Bar icons, let me take large and then command. Okay, here is the font size. So let us call it 14 and let's see how it is. Okay, I think now it's good enough. Okay, yeah. Yeah. So what we'll do is I'll just clear the screen here, CLC, and I'm using Octave, right? So here the goal is, okay, why is it still so? Edit preferences. Command, what about editor? Line length. What about font size? It's not there. Okay, here it is. So let's bring it to say 12. Let's see how. Okay, I think 14 would be suffice. It would suffice. Done. Okay. Okay. So I'm planning to determine trajectory for a projectile in space, in say space, so to speak. Yeah. So before we start, we always would like to clear all the variables and close all the open, say figure windows. So from here now let's start. So we'll define initial values or initial parameters, or say define just parameters. Now, as per what we learned is we have which parameter we have, say V, capital V, which is the initial velocity. Let me take to be say 10 meter per second, and the unit is meter per second. Let me call it velocity.
So when you write code, you must always make sure that you comment, always write proper comments. And then we have theta. So theta, let me call it as say, let me start with 30 or say even 45 degrees. And I would prefer it to convert into radians because that's how software works. And it helps I mean, it's usually removes any ambiguity, isn't it? And then this is just nothing but like projectile angle, initial angle of the project, or say velocity direction. I think that will be a better word. And this in radians. And then G, as usual, is gravity, which is 9.18. And I'll just call it acceleration due to gravity. This is meter per second square, meter per second square. Right? So I'm just listing down the main components of the small script that we are writing. Compute trajectory. Then we'll have plot the trajectory. Right. Now for computing the trajectory, we require some function. So define function. Right. So this is the first thing that comes in our mind. And recall that we can when we use softwares like and such to integrate something. So say I'm just looking at the help window of this and let it okay. So this is how to use ODE 45. So they want us to give some values, and what happens in general is that we are always required to give all the variables in I mean the parameter, I mean the quantities that we would like to solve in some sort of a vector like format. So in this sense, what it would be is when we define function, now let's give us an what we call as displacement x displacement. Let's call it as say z variable z1, the first element of this or likewise, why don't I call it z is equal to z is a vector whose first element is x, second element is y, third element is vx, and fourth element is vy. So this is equivalent to saying that x is equal to z1, and I don't know whether I should use capital. Just let's use small z, right? And then y is equal to second element of z, second component of z, and then vx is equal to third component of z, and vy is equal to fourth component of z, right? Now let's define our function. So in MATLAB, MATLAB or Octave, we can also define something called as an inline function, and we'll be defining inline function, which we can directly specify here. So let's call it trajectory. So trajectory is a function. We call it as name it as is a function, and it will have two arguments, t and y, and t and z, because that's what we are doing here. And then based on what we did, the first we had dx by dt is equal to vx, right? So vx is essentially third component. So we have z3. Now we had second equation was dy by dt is equal to vy. So vy is the fourth component. And the third equation was dvx by dt is equal to 0. So which means that is just 0. And the fourth equation we had is dvy is equal to vy by dt is equal to minus z. So we'll have minus c. And with this, we are able to close this. right? Now, let's go back to the Octave help window. So it says us, how do we use this OD45? So it says that you have to have ty is equal to OD45, give the function, give the range over which you would like to compute the time, to solve the function, and give some initial values, which is necessary, right? And let's look at what all adjacent functions it gives about, say, options that we have eventually. Okay, what is it? Fine. Okay. 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 So there are some of the functions which, so now we have defined the function. Now, say we have initial conditions. So for initial conditions, let's put it in a vector called z naught. And the initial condition for x starts with 0. I mean, it has a value of 0. Initial condition for y is also 0. For vx was again v into cos theta. And for the vy, it was v into sine theta. Right? So we are able to have this. This is clear. Now we can define how long we would want to solve it. And then what we had talked, right? Talked about it was TF. So TF was the final time. And it was, we had calculated it numerically as 2 into V into sine theta by G, right? So I'll call this as a final time. Fine. So this, till this point, we are going to solve the problem. Okay. And it's again in seconds. Now we can start solving it. And again, by default, T naught is equal to 0. T naught, which means that initial is 0. So now we can solve our problem. So we give T comma Z is equal to ODE 45. And then let's just have a look at how they provide the function for an inline function. How do they? Okay, so they just give the function name. Fine. So the first option is T range and second is initial condition. Fine. Okay. So we have function as trajectory. So first was the T. So I'll just give this starting and final values for what's how long we would like to solve it, and then the initial condition, which is Z naught. And I think with this it is solved. So let's try running it. I think things are all in order. So here it will be actually say determine solution. Now let's say run it. Let's see what it gives. Does it give us any error? Okay, doesn't seem to so, right? No error, it's given to us as of now. Fine. So once we have, now just take a look. Now Z, as you see here, it has a dimension 4. Now you'll ask why it has a dimension 4. The reason is that you have first column as X value, second as Y value, third as Vx value, and fourth as Vy value. And you can clearly see even during numerical when we solve it. So X keeps on increasing. Y also, as of now, it keeps on increasing, but again, it will decay. But Vx is always constant, which we again know from an analytical solution. And Vy keeps on decreasing till reaches 0 and then starts gaining pace again, isn't it? So this we have, right? Right. Now it has, I think, done a very it's a very distantly spaced. So one way of mitigating this issue is that what I can say is I want to define my own time array. So I'll call it T array, and you'll use linspace for this. And I'll give T naught as the initial value, TF as the final value, and I'll ask it to run for say 100 time steps. And this is what I'll put here, T array, and run the simulation again. Right, so it's now 100. So this just because I wanted some finer information about these details. Now what we do is we'll plot, and before that let's collect our trajectory. So now we'll say that extract information. So how we extract is x is equal to z first column, which means that everything first column, right? Y is equal to everything second column, and Vx is equal to everything third column, and then Vy is equal to all components of the fourth column. Now we are all get set. Now let's plot the trajectory. Let's have a look at how our ball, say, moves through the space before it lands back to the lands on the ground. So let's have K, which means a black line. Give some, say, line width. I hope this works in octave. And width, and I can give some value, say 2. Now let's just and also give some label, X label. And this I'll call it as X as in terms of meters. And so Y label as well, Y in terms of meters. Now let's just plot, see how it goes. See, now this is what we would have expected from a trajectory, right? So this is how it's behaving. Fine. Now let's also plot so the title of this plot will be, let's give it a figure, some figure. The title is trajectory. Right. Now this is some second figure. And or maybe what I'll do is let me combine everything in one place. Subplot. Let's have a 2 cross 2 and the first element. And this we call it as why not have just one? And this here we have as second element. And now here what we'll do is we'll plot T, which is the time variable, time array, comma Vx, because we want to look how it shows, and then K is color bar, and then hold on. And then I'll also give some name. I hope it works. Display. Vx. Right, let me just see whether it runs. Okay, this seems to run, but before that, let me just also have something called as legend. Let's see what it gives. Okay, it does so. Okay, it does so legend. And then what we'll have is hold on. right? And then we'll have second plot, Vy. And let's also have some labels. So X is time and Y is, I'll just call it velocity components. Right? And then let's have lesson. Now let me run it and just see what it gives. Now you see. This is what happens. So we started our ball from here. It took all this path and reached here. And for velocity, as we had saw from analytical solution, that velocity will always remain constant, and it did remain constant. However, that was the X component, and for Y component, it seemed to decrease, reach some value 0, and then drop down. Better to have some grid in our plot. So this will usually helps us to really differentiate. Yeah, so this is how it is. So see, at 0, it reaches its value at somewhere in midway and then drop. So this is what our aim was for today. And these all codes are available in the folder that I have shared, or even accessible through NPTEL platform. So with this, I'll just stop sharing. And we'll close the session for today. If you have any doubts, please let me know during the next tutorial session. I think I'll just close the session for today. Yeah, and yeah, let's meet again on 13th September. Okay, so bye everyone.